is always equal to lambda into N. The energy released per fission is 200 MeV. The products formed are barium, krypton, 3 neutrons plus a large amount of energy, and helium nucleus is 1.1 MeV and 7 MeV respectively. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. Continuing my discussion on the topic nuclei. In yesterday's session, we have solved numericals from this chapter. I hope you have gone through this session. You have solved those numericals and you have come prepared for today's class. In my today's class, I will be working out few more important problems from this chapter. All these problems are 5 markers appearing from the previous papers. The first one, I have been asked to find the activity of 1 milligram of radon-222. Activity of 1 milligram of radon-222 whose half-life is 3.825 days. So I will be calculating the activity of 1 milligram of radon-222 whose half-life is 3.825 days. So my dear students, if you recall the concept of activity, what we called as the number of disintegrations per second. What was the expression for activity? Very good. We told activity A is always equal to lambda into N. Remember this? Activity of a radioactive sample is always equal to lambda into N. What is lambda? Decay constant. N, number of atoms present in the given sample. Again, I repeat, what is lambda? It is the decay constant. What is N? Number of atoms present in the sample. So, my first attempt here is to find out lambda. How do I find out lambda? I know half-life. So, lambda is 0.693 by T. So, the problem says half-life T is 3.825 days. Now observe the data. Half-life is 3.825 days. But SI unit for time, seconds. So this becomes 3.825 into 24 hours into 3,600 seconds. 60 minutes into 60 seconds. So I have converted half-life in terms of seconds. Next. Now we know that lambda is 0.693 divided by T, decay constant. So lambda is 0.693 divided by 3.824 into 24 into 3,600. Simplify, so much per second. I want you all to take out your calculators, do the simplifications. I'm giving you all the concept. I'm giving you all the idea. So the first part of the calculation is done, where lambda is calculated. Now I have to calculate number of atoms in the sample. So, if you observe, the given sample is radon 222, from which I am calculating the activity of 1 milligram of the sample. 1 milligram of radon 222 activity has to be calculated. So, 222 grams of radon has how many atoms? Any given mass has Avogadro number of atoms. So 6.023 into 10 power 23. I have to find the number of atoms in 1 milligram of radon. So 1 into 10 power minus 3 grams consists of how many atoms? So we say N equals 6.023 into 10 power 23 into 1 into 10 power minus 3 divided by 222. Do the simplification. So many atoms. So the first part of the solution, calculating decay constant. Second part of the solution is to calculate the number of atoms in the sample, so that now A equals lambda n. Substitute, you'll get so many disintegrations per second. All calculations, simplifications, as a practice, I want you all to take up. Adrile SI unit nodi, disintegrations per second, which is the unit in which activity is expressed, Curie. So here, whatever answer you get, X, divide by 3.7 into, finally you get 153 Curie as the answer. This is to convert the given unit into Curie. Simple. The next one, students. So we have to calculate the energy released in MeV, million electron volt, by, this is important, 1 gram of uranium-235. Energy released by 1 gram of uranium-235 in the following fission reaction. A fission reaction is given. Uranium-235 92 bombarded with a slow-moving neutron. The products formed are barium, krypton, 3 neutrons plus a large amount of energy. A standard equation showing us a fission reaction, from which I have to calculate energy released by 1 gram of uranium-235. To begin with, I will consider the mass of uranium-235 and a neutron before collision. So first, I will consider the mass of uranium-235 and 1 neutron before collision. So this is equal to, mass of uranium is given to be 235.0439. 235.0439 plus mass of 1 neutron. So mass of 1 neutron 1.0087. So this is 1.0087, which is equal to 236.0526 units. So this is the mass of uranium-235 plus 1 neutron before collision. Next, mass of products after collision. So now, mass of products after collision. What are the products formed after collision? Or you can say after fission. This I will also use before and after fission. Barium, krypton and 3 neutrons. So mass of barium 140.9178. So this is barium 140.9178 plus krypton 91.8854, 91.8854 plus 3 newtons 0087. So this turns out to be 235.8293 units. So if you observe, students, this is the mass of barium and 1 neutron before fission. Mass of barium, krypton and 3 neutrons formed after fission. ವ್ಯತ್ಯಾಸ ಇದೆಯಾ ಮಾಸ್ ಅಲ್ಲಿ? Yes. What do you call that as? Mass defect. So mass defect here, delta M equals, so 236.0526 minus this, so mass defect is 0.2233 units. This is the difference in mass, the mass defect before and after fission. Now, energy released when one nucleus of uranium-235 undergoes fission. When one nucleus, I'm not considering the given sample, one nucleus is undergoing fission. So that is equal to 0.2233 into 931 MeV, which is nearly 207.9. So if you observe, I had to keep the answer in MeV, but I have to calculate the energy released by 1 gram of uranium-235. So this will be 1 into number of atoms in the sample divided by 235. So energy released by 1 gram of uranium-235. So the answer will be 5.33 into 10 power 23 MeV. So this will be the simplification. Again, students, a nuclear reactor consumes 4 kg of uranium-235 per day. Per day, it is consuming 4 kg of uranium-235. The energy released per fission is 200 MeV. What is the power output? Now, the problem says there is a nuclear reactor which is consuming 4 kg of uranium-235. 4 kg of uranium-235 or 4,000 grams of uranium-235 per day. And he says, energy released per fission. So, energy released per fission is 200 MeV. 200 into 10 power 6 into 1.6 into 10 power minus 19, which is 200 into 1.6 into 10 power minus 13 joule. I have to calculate the power output. So now, how do we calculate the power output? It is very simple. Again, number of atoms in the sample, 235 grams of uranium-235 has Avogadro number of atoms. What is the mass given for us? It is 4 kgs, or I say 4,000 gram of uranium has how many atoms? Which means X is 4 into 10 power 3 into 6.023 into divided by 235. We have so many atoms. So I have calculated the number of atoms in the sample. Therefore, energy released per fission will be so many atoms into 200 into 1.6 into 10 power minus 13 joules. Number of atoms you calculate in the sample, multiply by, yes, energy released per fission. So this gives you energy released per fission per day. So what will be the power output? So input power by output power. So the power output has to be calculated. This will be an assignment for you all. I've given you the key steps. The last step, think over, go to the definition of power, you will arrive at the answer. So the next one, the binding energy per nucleon of deuteron H12 and helium nucleus is 1.1 MeV and 7 MeV respectively. If two deuteron nuclei react to form a single helium nucleus, what is the energy released? Now, binding energy per nucleon of deuteron is given to be 1.1 MeV. This is the binding energy per nucleon of the deuteron nucleus. Therefore, binding energy of H12 deuteron is 2 into 1.1, which is 2.2 MeV. But how many nuclei are forming? 2 nuclei. Therefore, binding energy of 2 nuclei of H12 is 2 into 2.2, 4.4 MeV. Which is the single nucleus formed? Helium. So binding energy per nucleon of helium-4 is 7 MeV. So binding energy of helium-4 is 4 into 7, 28 MeV. What does that have to calculate? Energy released. Very simple. 28 minus 7, nearly 21 MeV of energy. So in today's session, I have solved 5 markers from this chapter, continuing a few more competitive problems will be solved. Until then, have a nice time. Thank you.